your exam, so I thought we'd take just a few minutes, run through some of the things that we do in class, i.e. go through page by page, just reminding you of, well, what you should be focusing on. One good thing to always look for are your objectives. We don't necessarily hit all of them exactly as written, and we add to them frequently, but it's a nice place to start. Just a heads up on some of the things you should be able to do. Now, Chapter 17 starts the material, and it begins with the electric charge. You should know your properties of electric charge. Right now, if I were me, I am me, if I were you, I would have my book. I'd be kind of looking through as we go along, making some mental notes about these sort of things, or if you have the digital copy, perhaps looking at that. Charge, make sure that you know, of course, it's something we can't see, we can't taste, we can't touch, etc., etc. There are two kinds of charge, positive, negative, and, well, unfortunately, looking at something that's charged, I've got no idea. A, it's charged, or B, what type of charge it has. The only way I can tell is by how matter reacts in the presence of it. So, for example, we see figure A down here, the girl with the balloon and her hair. We know this is a charged situation. Why? I have electric forces of attraction. That tells me A, I've got charges, and B, it tells me that they are unlike. So, unlike charges attract. Figure B here, again, I have a force, but I have a force of repulsion. So, when objects repel, they have like charges. So the only way I can see that something is charged is by the forces that it creates. And by the behavior of the matter in those forces, I can tell whether the charges are identical or whether, or at least like, I shouldn't say identical because that also implies magnitude, but like versus unlike. Don't worry about good old Ben Franklin, but you can always give him a nod that he gave us our positive, negative attributes, but as we said, that's not really terribly important. If suddenly electrons we called positive, the world would not change at all. However, be very sure you understand the idea that charge is conserved. The law of conservation of charge says whatever charge you got, someone else lost. So if you gain a negative 5 charge, 5e, someone else lost 5e of charge. Now, by and large, when we're talking about charge for our purposes, we're dealing with the idea of electrons. Electrons we know are free to move far more easily than the particles in the nucleus. Therefore, when things become charged, it is because we have transferred electrons to it or we've taken electrons away from it. In terms of Millikan's experiment, you should know that he found that charge is quantized. It's a discrete, specific value, and that value we know, it's not a secret, 1.6 times 10 to the minus 19 coulomb, which is the charge of a single electron, and it's also the charge of a proton, except the electron we call negative, and the proton that we call him positive. So you should not necessarily remember this value. Don't memorize that particular value right there. Of course, it's on your formula sheet. But you should know what it represents, and you should know when to use it. If you're given a charge, and sometimes you are, just in terms of E, you should know it's whatever the number is, 1, 2, 3, 1,000, 100, a million, times the fundamental charge, 1.6 times 10 to the minus 19 coulomb. And don't forget your unit coulomb is associated with charge. Beyond that, his whole experiment right here, no, don't worry about that. That's not really relevant. Just know charge is quantized. Know we got the value here. And of course, it's quantized because we are passing electrons back and forth, and you can't pass half electron, quarter of electron, etc. You should know the difference between conductors and insulators. What's going on with the electrons in each that allow conductors to have electrons moving very freely, but insulators having them very restricted in their motion. In terms of the semiconductors and the superconductors, just know the definition. Okay, we're not going to really go into them heavily. We might hit superconductors later in some further chapters as we go along, but for right now, just know their basic definition. But do be very clear on what's going on with these two guys. Now, in terms of transfer of charge, make sure you know friction, conduction, and induction. What are the results of each type, and what goes on with each type of charge transfer. So those three methods of charging. Be very, very, very clear on it. Your book kind of skirts along the friction method. I mean, it jumps right here into the idea of this process is known as charging by contact. The idea of conduction is really kind of more described by that. But here, bringing back the idea of the balloon and the hair being charged because they rub together, that's an example of the friction method. Two things start, neutral, rub them together, they get equal and opposite charges. And we talked about the triboelectric series, that we could predict who would become the positive, who would become the negative. Don't worry about that. You wouldn't be asked to, between a pair of materials, tell who became positive or negative. But do know that in the friction method, rub two things together, one becomes positive, one becomes negative, and the magnitude of the charges are identical. Now, in case of the conduction method, we're actually starting with something that actually has a charge. Something has been given a charge, and that's actually, they're jumping right into induction because they love induction in this chapter. They just absolutely adore it. And I'll talk about why in a second. When we're looking at the idea then of that conduction method, we start with something that is already charged, bring it to something that's neutral, and by touching it, we can now make that neutral object charged. Remember though, when we are dealing with the idea of conduction, whatever charge you bring to the party, that's the charge that my neutral object will get. So, if, what is a tiny little pen, I have some neutral object, I'll make it a box, and I bring a rod towards it that I'm going to give a negative charge, simply because dashes are easier to draw with my mouse than pluses. And I allow these two to touch. Bing! The more positive box, even though he's neutral, he's still more positive, electrons flow onto him. And then when I take the rod away, boom, the electrons are stranded. So whatever the charge of this object is, that's the charge this guy is going to receive. Electrons always going to the more positive object. So friction, two things start neutral. Conduction, one thing has to start with a charge. And the same thing is true when we then get to the idea of induction. In induction, what I'm going to do is take something that is absolutely neutral and just bring something close to it, brought near, without touching. And we emphasize that in some of the labs that we did. I said make sure you don't touch the two together. When you have induction, and here's why your book kind of goes a little crazy on, whoa, that kind of like slid in a very strange and ugly fashion. Well, you know, it's me, so there you have it, strange and ugly. Pointer options, highlighter. Okay. When we're dealing with these spheres and rods down here, well, that's much better. The reason your book goes heavily into induction as opposed to the other two methods is because this really emphasizes the action of electric forces. That when we have, in this case, an object that is charged, we bring it to something that is neutral, the electric field, which we go into in some detail a little bit later on, that surrounds my charged object, will promote forces in the neutral object. This is a negative charge, it's going to repel my electrons. So even though I have the same number of positives and negatives right here, the electrons get sent to one side of the sphere, and the positives are left on this side of the sphere. So the surface charge that's produced by induction is always opposite that of the charged object you bring. The guy's still neutral, my sphere hasn't changed, however, I have created a polar situation, and we talked about how you had gone over that in chemistry. Now what this diagram shows, and they bring this little figure in right here, and I didn't go over it really in class, but that's a grounding rod, that's a grounding situation. If I was to suddenly touch a conducting wire to this particular sphere, those electrons would race down that wire. And take the wire away, electrons have been depleted, and now he is not just polar, he is now actually positively charged. So that's an extra step to induction. That's not the induction process necessarily itself. This is the induction process right here in figure A. Okay. But if I wanted to make this guy charged, truly charged, I could go ahead and give the electrons a place to run. And so your electroscope, where we used induction to um, move the charges in the aluminum foil to the opposite side of the foil as your balloon, we gave them a conducting rod to follow down. So we were actually doing that step in the electroscope, though we didn't go into that in quite as much detail. So you did this basic type of thing right here. Okay, you did this little experiment right up here, um, except you used a balloon and some little pieces of foil. Induction, we don't have to have things touch. We can still see the electric forces at work causing the motion of matter. Coulomb's law, please make sure you know Coulomb's law. Know what it says in terms of how does both charge and distance affect what's going on with your electric forces, and be able, of course, to work the formula. So expect an inverse square type question, just a generalized inverse square type question, and expect to use that formula in problem solving. Coulomb's constant, again, not something we have to actually worry about. Okay, so don't worry about it in terms of memorizing it, but do make sure that you use it properly in your formula. Now, in terms of solving problems with Coulomb's law, we started with some pretty simple ones with just pairs of charges. You might ask to solve for something about the size of force. That's, common. You might also, however, be asked to solve for something about distance, like this guy right here. And some people got a little, stumped with the idea of how many electrons or excess protons were available. That's not really a factor of Coulomb's law. That's just how much charge do you have. But make sure you can go from charge in Coulomb to number of excess electrons or excess protons. Electric force is a field force. Not surprising, therefore, that his formula very similar to the one we saw for gravitational force. It is an inverse square. It's dependent upon the property of matter that creates the force, in this case charge. It's why induction can actually occur, etc., etc. And here, of course, is where people first started to actually weep large tears. The idea that this is a force, and all forces are vectors. I don't care what type of force it is. So we had to go back to those vector techniques and the principle of superposition, i.e. adding forces together. However, if it was a vector, and these guys are, you can't just add one to the other. You have to consider what is happening in terms of the y direction. Wow, that's a beautiful representation of the y direction. And what's happening in the x direction. So you had to look at the sum of the x and the sum of the y. Now, for CP, you pretty much were restricted to charges on a line. So the most problem solving we did, though we did hit, like a little bonus, oh hey, see if you can challenge yourself and do that, where they weren't in a line. But for you, I would be very, very, very sure that if I gave you a target charge on a line, you can tell me the net force. So run Coulomb's law between that charge pair, Coulomb's law between that charge pair. Ask yourself direction based on what are the charges involved. Let's say something like that. So between this charge pair right here, force would be this way on that target. Between this charge pair, it would be that way. So therefore you would subtract them. Now, honors, you did this problem too. However, you also did some like this. So absolutely expect that you're going to find some vector problems, and I would bet you bottom dollar, even money, yeah, one of them is going to be where they are not in a line, and you do have to resolve one vector into its components. So we had these types of problems. Again, for CP, concentrate kind of more along this line. However, honors, you've got that in your pocket as well as something like that. In terms of equilibrium, CP we didn't get into it, so this is really not a topic for you. Honors we did. Not heavily, but the idea of equilibrium, I can place a charge somewhere in a system, right there, where he will experience zero net force, and the question is, what is that position? In terms of solving these, remember, set the force between that charge pair and that charge pair equal to each other, because they would have to be equal and opposite in order for this to occur. The key was how did I set distance, choose one charge pair, in this case between charge 3 right here and 2 right there, as the target distance, and then for the other charge pair, take your total distance between the two non-target charges and minus the target. So that's how we set up the distance. So you were basically coming down to a series of equation or an equation that looked like this. Right? So make sure, you could be asked an equilibrium question. They're not that difficult. The issue is simply making sure that you do properly set up the phrase for position. Oh, don't worry about that. Mrs. Coulomb might have cared about Mr. Coulomb's torsion balance experiment. We don't. Electric field? Know, of course, that electric field is why we have a field force. Electric field, where's my cursor? There he is. Region in space around a charged object, blah, blah, blah. You should know one way we look at it is that it's the sum of all the force vectors acting upon a charge. And that little charge, Q sub 0, is a small positive charge that we call a test charge. He is very tiny, so he does not disrupt the overall situation. And he is by convention positive. So when we then turned around to draw the lines, the direction of the electric field, it was based on the fact that we're testing it with that positive test charge. Therefore, the electric field in this situation pointing away from the test charge. Why? Because that's the direction the force would point. The electric field in this situation pointing towards the negative. Why? Because that's the direction the force would point based on a positive test charge. So when we're looking at drawing field lines or looking at the direction of the electric field, think about which direction would it point? Away from a big positive charge, towards a big negative charge, and that came in handy when we had to actually solve some problems with electric field. Know that at least one of his units is the Newton per Coulomb. Volt per meter is actually another one we get to later, but Newton per Coulomb is his appropriate unit. And when we look at the idea of electric field strength, know that, not surprisingly, it depends upon both charge and distance. So the size of your charge determines your electric field strength. Bigger charge, bigger field strength. Distance, the farther you are from the object generating the field, the weaker the field strength becomes. So our basic ideas of what's going on with strength, force strength, now field strength, that same sort of general pattern is going to apply. This particular formula you should be able to work with, of course, and it's based on a point charge. So if I have a proton, I have an electron, I have just some little point in space. What's the electric field at a certain distance from that point? Use that formula to solve for it. Don't worry about sample sizes of electric fields. That's not an issue. But oh yeah, electric fields are vectors. And so for solving electric field strength, we did have to break, sometimes, fields into x and y components. Again, this is another example where we had a little bit of difference between our CP and our honors. CP, again, you were pretty much restricted to charges in a line. You might have these charges, and then you're asked, what is the electric field at this particular point on my number line? And so what was the field strength based on that charge? Not only strength, but also direction. Field strength and direction from that charge. Field strength and direction from that charge. So using my formula, KQ over R squared, you ran it for each of those three if it was 3, 5 if it was 5, or 2 if it was 2 charges. And then summed them up based upon the direction of the fields. Did you add them together because they were in the same direction? Did you subtract them because they were in opposites? Honors, we did throw in those some like this. Okay. CP got a couple for practice, but I wouldn't, if I was a CP student right now, I wouldn't be concentrating on this. I'd be concentrating more on this example. Honors, make sure you can handle this example as well. In fact, for both of you guys, I would expect a combo question. Given a series of charges, what is the electric force on a certain charge? Same diagram. What is the electric field strength at a certain point? So a couple questions you had did that. It combined the two together. I would expect that to show up probably as one of your problems at the end of the multiple choice section. In terms of electric field lines, you should absolutely know that they are not real. They're not physical lines. They are a visualization technique. You should know number of field lines proportional to electric field strength, so more lines means stronger field, and the more densely packed the lines are also indicates a stronger field. We should know that when you are drawing your lines, they point away from positives and they point towards negatives. So I could just simply give you a picture that looked like this, but it did not have on it the type of charge. You'd have to tell me that was positive. This guy's negative. And I might give you two charges and ask you, tell me the type of charge of each and tell me which is stronger. Well, which one's got more field lines? And that's going to be the stronger charge. Field lines never cross, and so when I bring charges together, that provided situations like this versus this, the like versus unlike charges. That actually gave you, again, a visualization of what was going on and why unlike charges would tend to attract versus like charges repel. In terms of conductors and electrostatic equilibrium, what should you know? Excess charge on a conductor goes to the outside. Charges space themselves as far apart as they possibly can, and that's going to be the external surface area. Electric field just outside a conductor is perpendicular to the conductor surface. If not, we'd have this situation, and that would set charges in motion. We'd have electric current. These guys don't have electric current flowing through them. So the field has to be perpendicular so that no component of the field is actually horizontal, pushing the charges one way or the other. And on an irregularly shaped conductor, charge tends to accumulate where we have the sharpest points. And we talked about why you don't want to be standing in a field or under a tree or holding up a golf club and the idea of a lightning storm. Van de Graaff generators, oh, don't worry about that. But again, something like this could give you a picture. Where is the field strength strongest? Which end would be most likely to be hit by a spark or give off a spark? You should know, of course, it's this end as opposed to the other end.